Hello, these are the solutions to activity 10. So which ion below contains two unpaired electrons in its ground state electron configuration? We'll just look at nickel 0 for a minute. What you want to do for a cation configuration is start with the neutral atom. So nickel would be an argon 4s2, 3d8. And we take the electrons away from the largest orbital first. And the largest orbital is the orbital with the highest n value with the highest L value. So highest n with the highest L. So highest n is 4. So we take those 4s2 away, so we get a 3d8 for nickel 2 plus, and 3d8, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 2 unpaired electrons. Lead 2 plus, so lead 0 is a xenon, 6s2, it's all the way across the F block, it's all the way across the D block, and it's back to the 6p2. So you lose the electrons first from the highest n, which is 6, with the highest L, which is 1 for this case. So we lose the 6p2 first. Now these were the 4 valence electrons of lead 0, so we lose the 6p2 first. So that would be 0 unpaired electrons. And then zinc is an argon 4s2, 3d10. Remember, it only has these 2 valence electrons. These aren't even valent, so we lose those valence electrons first. And that would have 0 unpaired electrons as well. So only nickel 2 plus has 2 unpaired electrons. Question 2, which ion below is smallest in size? So chloride or scandium, both of these have 18 electrons. They both have the argon configuration. Scandium has 18 plus 3, 21 protons. Chlorine only has 17. So the smaller ion here is scandium. We can roll out B and E. And then Li versus F. Li bigger than F, size decreases left to right, so fluorine is smaller. Fluorine is smaller. And then O2 minus versus O, add electrons to an atom. You make the anion bigger. O2 minus bigger than O minus, so O2 minus would be bigger than O minus, which would be bigger than O, so O is the smaller ion, smaller compared to oxide. So just O. Looks like answer A. Question 3. Melting points of ionic compounds are often found to be proportional to their lattice energies. Which compound below would be predicted to have the greatest melting point? The greatest melting point is a compound with the highest lattice energy. Highest lattice energy is going to be the compound with the greatest magnitudes of charge or the smallest ions. So plus 2 minus 2, plus 2 minus 2, plus 1 minus 1, plus 1 minus 1, plus 2 minus 1. So I'm going to roll out the plus 2 minus 1s and the plus 1 minus 1s, and I'm going to leave myself with the choice being one of these plus 2 minus 2s. Do I want the bigger ions or the smaller ions? Smaller ions more attracted together, higher lattice energy, higher lattice energy, greater melting point. Now, melting points aren't always directly proportional, so sometimes you'll see a break in this trend. But just for predicting here, the MgO would have the highest melting point of these 5 compounds. Dipole moment of Hi is 0.44 debye, bond length 0.61 angstrom. Calculate the charge on hydrogen relative to the charge of an electron, given that iodine is the more electronegative atom. So my Lewis structure would look something like this. You could start with iodine here, hydrogen here, forming that single bond. Iodine being more electronegative means this bonding pair is going to shade towards iodine, making it the partial negative element, hydrogen going positive. So I get this from the electronegativity difference. And so iodine should be partially negatively charged here. So this should roll out answers A and B. And then the way we can calculate charge is through the dipole moment mu. It's equal to Q times R. And so the only issues is that we have some non-SI units that are often used. We often use bond lengths in angstrom, where this is 1.61 times 10 to the minus 10 meters in SI units. and then 1 debye is equal to 3.34 times 10 to the minus 30 coulomb meters, where 1 electron charge, so the charge of 1 electron, is 1.602 times 10 to the minus 19 coulombs. These are usually given. They're on my practice quiz sheet. They'll be on the test somewhere if you have to do a problem like this. And so the way this problem works here is that we're going to try to solve for Q by taking mu divided by R. Mu is reduced. Mu is the it's a reduced mass, but that's a different context of a problem. Mu here is the dipole moment. So in physics, you might learn something about reduced mass. That's a different problem. Mu here is the dipole moment. And so the dipole moment is 0.44 debye. And then the bond length 1.61 angstrom. Only issue is we got to show how these units cancel. So let's convert into SI units. So 1 angstrom, 10 to the minus 10 meter. So hence 1.61 times 10 to the minus 10 that we set up here. And then the debye, 1 debye, 3.34 times 10 to the minus 30 coulomb meters. And I think sometimes we get a little confused on calculating this in coulombs. Imagine if this were ionic. If this molecule is ionic, then hydrogen would be plus 1 electron and iodine would be minus 1 electron if we went fully ionic. And so plus 1 electron minus 1 electron would mean iodine's charge would be minus 1.6 times 10 to the minus 19 coulombs. So we're predicting that the charge on iodine is somewhere between 0 and less than 1.6 times 10 to the minus 19 coulombs. Okay, and so if I calculate the number of coulombs here, let me we go 0.44 times 3.34 e minus 30 divided by 1.61 e minus 10. That is 9.13 times 10 to the minus 21 coulombs. So a fair bit lower than the charge of an electron. That's the only last conversion that we need to do. Is we just need to say the charge of 1 electron is 1.602 times 10 to the minus 19 coulombs per electron. Just using the charge of 1 electron. And so we divide this by 1.602 e to the minus 19, and it's 0.057, meaning the charge on hydrogen and iodine are 0.057, where one's plus, one's minus. Hydrogen would be the plus, iodine is going to be the minus. So answer C. So this problem here is just showing you that for a diatomic molecule, you can calculate or use a dipole moment and the bond length to get a sense of what the charges are that are being separated by the bond length in the atom or in the molecule. And then you can get a sense here that when you say something is polar covalent, that you have some partial charges developing on these atoms, as opposed to them being zero if these bonds were equally shared. Like if you take a bond between two chlorine atoms, you have Cl, the charges on these atoms here are exactly equal to zero. But you put like HCl, then all of a sudden we get some charge being distributed. We get hydrogen being positive, chlorine being negative. Which ion contains 24 total valence electrons? So when we go to sketch a Lewis structure, one of the things we usually do is we first add up the number of valence electrons. So how do we do this count? Well, nitrogen has 5 valence electrons, oxygen has 6. We just look at the periodic table. And then if we have a minus charge, we have to add an electron for the charge. And so this is 24 for nitrate ion. And then ClO3 positive charge, so chlorine has 7, oxygen has 6 times 3. And then we have to remove an electron for the positive charge. And so this is 24, 18 plus 7 is 25 minus 1, so that goes to 24 as well. So both of them have 24 valence electrons. Choose the more polar bond, and so electronegativity is increasing towards F. So Cl, Bri are dropping electronegativity. This fluorine's the most electronegative. So electronegativity is increasing left to right, and then decreases top to bottom. So fluorine's the most electronegative. And so if you go CnO, so the electronegativity difference between C and F is big. The electronegativity difference between F and Cl is pretty small. And so F and so the kind of most electronegative elements are NOF, and then S and Cl. They're actually in the same. So S and Cl are right next to each other. So these 5 elements are the 5 most electronegative elements. And so carbon's not a very electronegative element, so its difference with an electronegative element is going to be bigger. So we get a bigger difference of electronegativity, so a more polar bond for CF. ICl versus IBr. So the key is smaller difference of electronegativity, bigger difference of electronegativity, because we get a bigger difference in those electronegativities. So bigger difference of electronegativity, ICl more polar than IBr. Then NH versus OH, hydrogen's electronegativity is particularly low. So if you pair hydrogen up with something more electronegative, so the higher the electronegativity you pair something H up with, the more polar the bond's going to be. So you get a greater difference of electronegativity. So it should be CF, ICl, OH, CF, ICl, hydroxyl. Oh, there we go. Which halogen has the greatest melting point? So for halogens, we get the increase in melting point from top to bottom because we have non-metallic elements. Non-metallic elements have to induce those charges in themselves. They don't have the built-in charges like metals or ionic solids do. So ionic compounds get bigger, like LAF or cesium iodide. We get a weaker force here, stronger force here, but then being bigger for I2 is better than F2. So F2Cl2 gases, Br2 liquid, I2 solid, and this is just coming from being bigger is better in terms of the ability of iodines to interact with each other. Which substance, when dissolved in water, leads to the formation of a gas? The sodium solid does because sodium solid plus water forms sodium plus, we got to form H2 gas, and then hydroxide ion is a byproduct. And so here's our gas. Sodium oxide just forms in water. This goes to 2NaOH, no gas. So just one. The gaseous compound SO3 dissolves in water. What type of compound forms? It's an acid. We form something like H2SO4, something acidic when a non-metal oxide reacts with water. Metal oxides form basic solutions. 10, how many electrons are found in the central atom of PF3? So phosphorus, like nitrogen, kind of has this dot structure. Fluorine has this dot structure. So we're going to have PF3. And so this is our Lewis structure for PF3. So we get one lone pair. You can also do this. We'll see this as we go in the chapter. You take the valence count of phosphorus for 5, 3 times 7 for the fluorines. It's 26 total electrons we need to distribute. So we take phosphorus, single bond the fluorines, give them an octet first, and then count the electrons used. That's 24 electrons so far. The 2 electrons left over are placed on the central atom. So anytime you have electrons left over, they go onto the central atom. Then we can also look at the charges. So phosphorus has 3 electrons closest to it, and the bonds with the 2 lone pairs, or with the 1 lone pair, 2 electrons. So phosphorus should have 5 electrons surrounding it for neutral charge, and it does have 5 electrons surrounding it. So the charge on phosphorus is 0, and that just helps us see that this is the proper Lewis structure. We might be trying to minimize the magnitudes of formal charge if we could, in some compounds. So seeing that we already have 0 formal charges around here lets us know that this is indeed a good Lewis structure. 11, in the the structure below of that's nitrous oxide, which are the formal charges of each of the atoms from left to right. So the way, let me sketch this a little bigger. The way I would calculate formal charges is say formally cut the bonding pair electrons in half, forget about electronegativity. Just imagine that you have these kind of boxes for the three atoms and calculate the charge that each atom would bear with that number of electrons surrounding it. So for nitrogen, if you had this kind of electrons, would this be N0, N plus 1, N minus 1, etc.? Well, nitrogen with 5 electrons has a neutral charge. So we have one more electron, so we have 6 electrons here, so this is a minus charge. Oxygen here should have 6, has 6, so that's 0. Nitrogen here should have 5, has 4, that's a plus 1. So one thing you can do is say, well, how many valence electrons does the atom have in the periodic table minus the number of electrons closest to the atom in the Lewis structure. And so this is how we get plus 1 for the middle nitrogen, and then minus 1 for the outer nitrogen. Now there's this other equation in the book that says, take the valence count for the atom, which would be 5, minus 1/2 of the bonding pair electrons, so that would be a half times 4, and then minus all of the non-bonding electron pairs, so that would be 4. So 5 minus 2 minus 4 is minus 1 for that first nitrogen. If we do this approach for the second nitrogen, we'd have 5 minus a half times 4 minus a half times 4 for the two double bonds. So there's two ways of drawing a box, cutting the bonding pair electrons in half, keeping the non-bonding pairs on the atoms they're attached to, and then just counting and saying, okay, if I have this for O, what's the net charge? Just counting up the electrons. 6 should have 6, so that's where we get neutral. So minus 1 plus 1, 0. Which is valid for ClF3. So ClF3, I think this is probably easiest done with, the approach of 7 for chlorine, 7 times 3 for 28 valence electrons. So I take chlorine, single bond my fluorines to it. Like I don't automatically give chlorine an octet. I just start with the fluorines, give them an octet. That's 24 electrons total. There's 4 electrons left over. They go on to the chlorine. So I should be choosing a chlorine with 2 lone pairs. We're not connecting in chain the fluorines. I don't have the right number of lone pairs. Wrong number of lone pairs here. You can also count A and B and see 28 electrons are not distributed. We could also calculate formal charges. We get 0 all the way around. We have 7 minus 7 for fluorine, and then 1, 2, 3. So if I break these bonds in half, I get 1, 2, 3, 4, 5, 6, 7. So the middle chlorine 7 minus 7 as well. Okay, that's all the questions on this activity. This kind of spans sort of the first half of chapter 8. So the next activity will have the rest of chapter 8. And I think it actually has all of chapter 9 on it too, and ends up becoming like a 2-week activity. So this is activity 10 for Thursday, end of October into November 1st. All right, guys, thanks for the attention.